Hope everyone's doing well today. So, we've already finished everything in as far as content goes in preparing for this exam. So today we're just going to go over review materials for this test. So I posted a list of review problems last time on two different pages, page 511, which is the chapter review, and then also page 481, which I think that was the work problems. I wanted to choose a few specific questions there. Oh no, that was probably the arc length problems actually. Anyway, let me find this. Let's see. So today we'll just go through and work some of these different review problems. We'll start with the problems on page 511. And so I ended up assigning, looks like 12 problems for review. Probably you can expect somewhere in the neighborhood of 9 or 10 problems on your exam. I already mentioned that there will be two parts to the exam, the in-class portion and a take-home portion. And this is probably the only test we'll have to split it up like that. But for the in-class portion, that'll cover the section 7.1 through 7.4, and then the take-home portion would be 7.5 and 7.6, which is on the work problems and the centers of mass problems. Okay, so let's go through some of these, or all of these actually. I think we'll have time. This is on page 511 that we're starting. And we have number 1. We're given the equations y equals 6 minus 1/2 x squared, y equals 3/4 x, x equals -2, and x equals +2. Okay. And so the instructions here, we want to find the area of the enclosed region. All three of these the first three problems, 1, 5, and 9, are all the same instructions. So step 1 is always to graph what we're looking at. So 6 minus 1/2 x squared somewhere between 3 and 4 is where that crosses the axis down here. So we'll draw it like that. And then y equals 3/4 x is a diagonal line that goes up 3 and over 4. Okay. Now, we're measuring from -2 to +2. So we're actually not looking at the entire enclosed region, we're just looking at the region between the top curve and the bottom line and between these two lines horizontally. And so we want to make sure that whatever information is provided us, we make sure we incorporate that into graphing and then setting up our resulting integral. Now, our limits of integration are just from the left side to the right side, which we already know is -2 to 2, thanks to what was being given to us in the problem. And when we calculate the area, we're going to take the function on top minus the function on bottom. So that means we'll take 6 minus 1/2 x squared minus the 3/4 x on the bottom, and we will integrate that and then evaluate it at the endpoints. Okay, so first off, we want to go ahead and integrate. And so integral of 6 would be 6x. 1/2 x cubed would, or 1/2 x squared would know the integral would be x cubed, and then that 3 will divide by 3, so it multiplies the denominator, so minus 1/6 x to the third, and then 3/4 x, it'll become x squared when it integrates, and we divide by that 2, so it'll be 3/8 x squared. And that's evaluated from -2 to 2. So if we plug in the x equals 2 first, then that's 12 minus, and then 2 to the third is 8 over 6. That reduces to 4/3. And then 2 squared is 4 times 3 is 12. 12 over 8 reduces to 3/2. Okay. X equals -2. We're going to get -12. We plug that in. Negative that is being cubed is still negative. Times this negative would make a positive, and this will be, what will that be? It's 4/3 again, right? Yeah. 8 over 6, 4/3. And then -2 squared is actually still a positive, but then still subtracted, so minus. And that'll be 3/2 once again. Okay. So we then combine our like terms together and we proceed from there. We want to be very careful about the minus sign because that does impact what follows. In fact, if you want to play it safe, you want to go ahead and distribute that minus sign first. That's not a bad way to proceed. Now, well, what we see happens is that our -3/2 and our +3/2, those will actually cancel each other out, but the others combine. So like 12 and 12 is 24. Minus 4/3 and minus 4/3 would be minus 8/3. And if we wrote that as an improper fraction, that'd be 3 times 24 is 72. Minus 8 is 64/3. Okay. At any point, if you have a question, please type something into chat and let me know if there's something I've done that you don't understand, or if you want clarification on. Absolutely. All right. So continuing from there, next we have problem 5. And in 5 we have y equals x and y equals x cubed. Yes. Now, this one's a little tricky, because if we look at the graph, y equals x cubed looks something like this, whereas y equals x looks more like that, although I could have drawn that a little bit better. I apologize. Gosh. But what happens is we end up with two different shaded regions that we'll have to find. There's one, and we have two different, actually we have 3 points of intersection between these two functions. If we set the equal to each other, we can figure out what these points of intersection are, and then that'll tell us what the limits of integration to use will be. Now I would say, okay, let's subtract their x left. That way we have a common x to factor out. And if we have x squared minus 1, then we know that's x minus 1 times x plus 1. So we get x equals 0, x equals 1, and x equals negative 1. Okay, so 0, negative 1, and 1, which probably we could have predicted what those are going to be, but I mean that verifies it, which is nice. So if the limits of integration aren't given as they are in this problem, we have to actually find them ourselves. So because we have two different shaded regions, there's two approaches we could take here as far as how to do this integration. One is we can do one integral from negative 1 to 0, where x cubed is our top graph and x is our bottom graph, and then do a second integration from 0 to 1, where x is our top function and x cubed is the bottom function. We always want to do top minus bottom, and in this particular case it actually switches at the point 0, where here is the curve over the line and here is a line over the curve. The other way that we could have worked this is, it turns out, even though I didn't draw it great, these two areas are identical, so we could just find one of those areas and then double it to account for the other area. Okay, so there's two different ways we can set that up. I actually like that second way better because we only have to do one integral that way. So we can say the area is 2 times the area from 0 to 1, which here would take the top minus bottom, so top is x, bottom is x cubed. dx. Okay, so we can either do 2 integrals or do 1 integral and then double the result to account for the other one. So we can't always use symmetry like this to help us out. In this case, because we know that it's symmetric, we can go ahead and do that. Alright, so integrating x minus x cubed, we know x becomes x squared over 2. X cubed is x fourth over 4. And we want to integrate 0 to 1. Now at x equals 1, we just get 1/2 minus 1/4. And at x equals 0, we just get 0 minus 0, because we just plug in zeros and they're both 0. And so we go ahead and subtract these two, so it's 1/4, and then 2 times 1/4 will be 1/2, and that is our area. Okay. Now again, the way that these problems will be presented on the exam, for instance, a problem such as this, you'll see the two equations, and I'll certainly have the instructions there. So the instructions might be find the area that is lies between the two curves. The area of the region that lies between the two curves, in this case, because it defines two different shaded areas, we have to consider that. More than likely, the one I give you on the test will not have this scenario where there's like two different areas. We have to combine them together. More likely, it'll be the case where sort of like number one, except I may not say -2 to 2, and we'll actually have to find the points where the two curves intersect by setting them equal, much like we did here. So it's elements of 1 and 5 put together where we have just the two equations, but setting them equal gives us the two limits of integration rather than 3. Okay, and we also want to look at 9. Probably only have 2 of these area problems on the test, not 3 by any means, but this gives us some different problems to look at. Now this time we have one that includes these trig functions, sine x and cosine x in this case. Now we want to be able to graph these, and as I recommended in other problems that involve trig functions, I would suggest making just a t-chart for each of the functions. Now, we know, and in cases where there's trig functions, I'll be sure to give you a range of values like this. So we know that we want to start at pi over 4, and we want to end at 5 pi over 4. So let's pick a few more values in between that we can plot. So we have pi over 3, pi over 2, maybe too much. Yeah, we'll be okay. 3 pi over 4, pi, and then 5 pi over 4. I could have included 2 pi over 3. I thought that might be overkill. In fact, I might scratch out the pi over 3. Because this at least will give us 5 values we can work with. And I think 5 values will be plenty as far as making sure we can properly define the shapes of the curves that we're looking at. In this case, the wave functions. So we plug in pi over 4. We know sine of pi over 4 and cosine of pi over 4 are both root 2 over 2. At pi over 2, sine of pi over 2 is 1, while cosine is 0. At 3 pi over 4, sine of 3 pi over 4 is root 2 over 2, and cosine is negative root 2 over 2. At pi, sine of pi is 0, but cosine of pi is negative 1. And at 5 pi over 4, we get negative root 2 over 2 for both values. Now it's worth mentioning that root 2 over 2 is approximately 0.71. So we'll need to kind of eyeball where this is on the graph. So next, we want to sketch. Okay. So we start off root 2 over 2, both of them start here, give or take. And then let's work on the sine first. Sine goes up to 1 at pi over 2, back down to root 2 over 2, and down to pi, and then to negative root 2 over 2. And so there's our curve for sine x. Now cosine of x starts here, then at pi over 2 it has a value of 0, at 3 pi over 4 it has a value of negative root 2 over 2, at pi has a value of negative 1, and then at 5 pi over 4 comes back to the same location. Okay. So now we can see exactly what we're looking at. And again, sine x is our top curve and cosine x is our bottom curve. Okay. So setting up our area, we take our integral, which is from from positive pi over 4 to positive 5 pi over 4. Take the top function, sine x, minus the bottom function, cosine x, dx. And that would be our setup. Now we go ahead and integrate sine x, which gives us a value of negative cosine x. We integrate negative cosine x, which is negative sine x. And we know to integrate from 5 pi over 4, or from pi over 4 to 5 pi over 4. So, plugging in those values, at 5 pi over 4, we know negative cosine x, and we already found these values in our table. Negative cosine of 5 pi over 4 would make that a positive root 2 over 2. And negative sine of 5 pi over 4 would make that a positive root 2 over 2. Then at pi over 4, we take negative cosine x, which is negative root 2 over 2. Minus sine x, which is root 2 over 2. Okay. And so what happens is we end up with root 2 over 2 plus root 2 over 2 plus root 2 over 2 plus root 2 over 2. So we end up with root 2 over 2 4 times, which is 2 times the square root of 2. Okay. So those first three problems dealt with area between two curves, and again, probably just two problems of those three from the test. I think you can expect one that has trig functions involved. So I would recommend following what I demonstrated here, which is to make sure, in order to graph these, we'll be given endpoints, and so we'll just make a t-chart starting with and ending with those two values, and then picking a few values in between that helps us sketch the respective graphs. It's always top minus the bottom, yes. And that's the key. So we'll make sure we get them in the right order. That's why we have to graph them in the first place, because we need to figure out which is the top function and which is the bottom function, and that's the whole purpose of the graphing. Okay. Now the next set of problems deal with volumes of revolution. Okay, I gave you let's see, 20, 22, 23, and I think it was just those three problems. Yes. Yeah, 20, 22, and 23. These are all on volumes of revolution. Now 23 actually has 4 parts to it, so really there's 6 problems here when all is said and done. Anyway, on the test, I think we can reasonably expect 4 problems on volumes of revolution. I'll summarize this later. So, but right now we have 2 on areas, 4 on volumes, and then probably 2 more on 1 or 2 more on arc length, and that would basically be the in-class test right there. So 7 or 8 problems in class, and then 3 take home. Okay. And what I'll do is I'll weight the problems equally, so however many. And this actually, if I just do 7 and 3, that would be great. I would prefer to do 8 and 3 though. Anyway, so if I do 8 and 3, then all the problems would be worth basically 9 points, and I'll give you 99 points right there. So. And I'll give you the last 1 point for academic honesty or something. I'll figure it out. Anyway, let's go ahead and look at these examples. So number 20, this is still on page 511. This is just the chapter review. Find the volume, and using the disk method, y equals e to the minus x, y equals 0, x equals 0, and x equals 1, and it's being revolved about the x-axis. Now whenever we see x and y equals 0, that means typically we're working in quadrant 1. Y equals e to the negative x, looks like this. And then x equals 1 would be here. And so that defines our shaded region, and it's being revolved around the x-axis. And it tells us we can use a disk method, but again which I think is K, not C, sorry. But we could tell it's a disk method in general because the shaded region that we found here is completely adjacent to the axis of revolution, so there won't be any space in between when we revolve that around. We'll just have a solid object. When we would use a washer method is if there is a hole in the middle being created, basically. Okay. Now our disk method says volume is equal to pi integral rate a to b of the radius function squared times dx. You will have the formulas provided as well. The main thing to focus on is knowing when to use the formulas and how to apply them, basically. Now, our limits of integration, a to b, is, since we're using our x variables here, we'll look at the x value on the left side and the x value on the right side of the shaded region. So it goes from 0 to 1. Now, our radius is the vertical distance here from the axis of revolution up to the curve, which is just the curve function itself, e to the negative x. And so we can say our integral is pi integral 0 to 1 of e to the negative x in parentheses squared dx. Now, before we integrate, we need to resolve e raised to a power raised to another power. And the trick there is that if we have raised to a power raised to another power, we just multiply those two things together. So it's actually e to the negative 2x that will be integrating. Now, with the integral of e to the negative 2x, we could do the shortcut there, which would be negative 1/2 e to the negative 2x will be the integral. But if you want to see the u substitution, we'll just say u equals negative 2x, just so we can have e to the u. And then du is negative 2 dx. Or we can say du over negative 2 equals the dx, or replaces the dx. Okay, so we end up with an extra negative 2 in the denominator. We'll move that outside with the pi. So we just have e to the u du being integrated, which we know is just e to the u. Okay. Replacing u with e to the negative 2x. That's from 0 to 1. Okay. Now, so we get negative pi over 2. Now, if we plug in the 1, we get e to the negative 2. And if we plug in 0, e to the 0 is actually just 1. So we get negative pi over 2 times e to the negative 2 minus 1. So we want e to the negative 2 minus 1, and then times, let's say, negative pi divided by 2. So if we wanted to, we could approximate this answer and say the volume is approximately 1.358. So this would be the exact value, and then this would be the approximated value. Both of those are fine. There's really nothing we can do to simplify this form right here. The only thing we might do is distribute the minus sign, but it doesn't really change much, to be honest. So we can leave it like that, or we can go ahead and approximate it. Either way is fine. Okay. Neither is worth more points than the other, so as far as grading goes, I'll grade these identically. So. The only catch is that for full credit, you must show all your work and then submit your work as an attachment to the question. And again, that's either a photo, if you want to take it with your phone, or and then you can attach it there, or if you have an app that scans documents on your phone, that works too, because it'll just send it as a PDF instead. Okay. So that was 20. Next we have 22. So we have y equals 1 over x squared, y equals 0, x equals 2, and x equals 5. In this case, let's see, we want to use a shell method, because this is in the instructions, but we're going about the y-axis. Now, anytime we're going about the y-axis, the shell method is probably the easiest, especially in this particular problem. It's going to be the easiest, but if we use the shell method around the y-axis, that means we can still use our x variables for everything and not the y variables. And that's an important difference to remember. The disk and washer method we can use for a horizontal axis and use our x's. And our shell method, if we have a vertical axis, we can use our x's there. Now, that's not 100% foolproof as far as an approach, but at least for this test it should work as far as the questions that I'll be asking you. So anyway, that's my recommendation there, at least. Horizontal axis, you can use disk or washer depending on which one it is. And vertical axis, we can use shell, and that should in general allow us to do at least 98% of the problems that we encounter in math. There will be sometimes we're kind of restricted to one or the other in a less optimal situation, but at least for the purposes of what we're doing, you don't have to worry about that. Okay. All right. Let's figure out what we're looking at here. First of all, going around the y-axis, we know that y equals 1 over x squared is this curve here. Although we don't really need the left half, we really just need the right half, because we already see x going from 2 to 5. And so that identifies our shaded region. Now, when we when we utilize a shell method, there's two different functions we need to identify. R of x, with the radius, and h of x, which is the height. So our radius in this case is just x. Now, remember we said the axis of or r of x is always the axis of revolution minus x, or x minus the axis of revolution. It really depends on whether the shaded region is on the right or the left of the axis of revolution. Because our shaded region is on the right of the axis, we take x minus the axis. Our axis, y-axis, is just x equals 0, so x minus 0 is just x. If our axis of revolution had been over here at 7, we would take 7 minus x to represent the shaded region. Okay, h of x, this is the height of our individual pieces here. Basically, h of x is the distance from the top edge to the bottom edge, so it's a lot like what we talked about in the first set of problems, is top minus bottom. And so in this case, it'll just be 1 over x squared minus 0. So just 1 over x squared, as it turns out. Now our formula for the shell method is 2 pi integral a to b r of x times h of x dx. So, in this case, we'll have 2 pi. We'll integrate from 2 to 5. Those are our limits on the x-axis. Now, r of x, we said, was x. H of x, 1 over x squared. And now we have dx. Okay. So we want to make sure we multiply these first. If we don't multiply these first, then we're not going to be able to integrate them correctly. In this case, x times 1 over x squared is just 1 over x. Dx. And we want to integrate 1 over x. And remember that the integral of 1 over x is natural log of x, and that is integrated from 2 to 5. So lastly, we just plug in our limits. 5 first, because it's natural log 5. I don't know what happened there. Minus the x equals 2 gives us natural log 2. And again, we could probably leave our answer just like that, or if we prefer, we could approximate it on the calculator. So that would be 2 pi times natural log. Where's my natural log button? A very good question. Oh, it's the one that says ln and log. Okay, natural log of 5 minus natural log of 2. And so it gives us an approximate value of 5.757. Okay. And so that solves our problem there. Now, in each of the cases, the disk method that we used in 20, and the shell method that we used in 22, again, both of them we were able to utilize the x variables and everything, which is nice because then we don't have to switch coordinate systems from x to y. And that's why I recommend for the horizontal axes problems we use disk and washer. If we have vertical axis, like we do axis here, like it's going around the y-axis, then we can use the shell method. Okay. Now, we'll get a chance to practice that further on the next problem, 23, which actually has 4 different parts. Now 23, we start off with just a definition of the shaded region, which is y equals x, y equals 0, and x equals 3. So we have y equals x is our diagonal line, x equals 3 is a vertical line, and y equals 0 is the horizontal axis. So that perfectly encompasses this figure. That's at 3, 0. So in this case, this is the shaded region that we're utilizing. But we have 4 different axes that we want to revolve it around. Now, for this, because the functions we're working with are so easy, like we're working with like y equals x, for instance, I'm going to set it up so that I'll set up each of the integrals. We won't actually carry them out because I think that work should be okay. But if you do have any issues with that, let me know and I can carry it further if we need to. So part A, we want to revolve around the x-axis. So we're going to take our shaded region, and I'm just going to draw the triangle now, not the extra lines. That's at 3. We're going around the x-axis. Now the x-axis is a horizontal axis, and the shaded region we're considering is completely flush against the axis. So our conclusion from that is we can use a disk method. Okay. Now the disk method, again, really just relies on us knowing what r of x is, the radius. The radius is this vertical component here, which is just from the top edge to the bottom edge, which this is y equals x, this is y equals 0, so it's x minus 0. So r of x is just x in this scenario. Now, we know our disk method is basically just pi r squared being integrated. So pi times the radius function squared, which we plug in our x for r. And then our limits of integration are on the x-axis, since that's where our variables are. So we go from 0 to 3. And so that's our setup for part A. And that's a pretty straightforward integral from there. It's just a power rule integration of x squared. Now on B, they want us to revolve around the y-axis instead. So this time we have a vertical axis of revolution, which means we want to use a shell method. Okay. So our axis of revolution is vertical, and so we'll use a shell method to approach this problem. Now again, with the shell method, we need r of x and h of x. R of x is the distance from the axis of revolution to each x value, which is just the horizontal distance, or x. H of x is our vertical component of the shaded region, so top minus bottom, which in this case is just x minus 0. So r of x is x, h of x is x. So our formula is 2 pi integral 0 to 3. We'll once again use the same limits of integration. And then we just plug in x and x for r and h respectively, dx. Now, on the exam, I may just have you set those up. I think I want you to carry them through, though, and go ahead and find the actual value of the integral. Anyway, yeah, I'll actually have you carry those through. On the final, though, you might find that we end up only setting those up just as a way to save some time. Because the final is cumulative, we don't have as much time to ask each question. So one of the ways that we cut that down is, for things like problems like this, we won't have you solve it all the way through once you get the integral set up. But at least for this first test, I want to see you work all the way through just to make sure everyone's understanding everything and comfortable with that. Okay, so part C and D, which gives us two different axes rather than just the x and y axis themselves. In part C, they want us to go around the line, was it x equals 3, which, there we go. Now, same shaded area that we've been using. We know it goes from 0 to 3. Now x equals 3 is actually just on this right edge of our figure. Okay. Now with this vertical axis, once again, axis is going up and down, we're going around that. We want to use our shell method to find the volume. Okay, now with the shell method, once again, we need r of x and we need h of x. Now h of x doesn't really change because h of x is just the vertical distance between the top and the bottom edge of the shaded region. That's still just x minus 0, so just x. Now what changes in this problem is the radius function. So now instead of the axis being over on the left hand side of the figure, it's now on the right hand side of the figure. So again, the rule that I gave you is you always take right minus left. Basically the shaded area is represented by x, and then the right or the left is represented by the axis of revolution. Now our axis is located at 3, it's to the right of our figure, so we'll take 3 first, minus x, representing the figure. Now once again, the idea behind that, if we pick some random value x, that means the distance from here to here is x. And if this is 3, then the distance between those two is 3 minus x. Okay? And this is the distance that we want. This is how far it is from the axis of revolution if it's on this right-hand side. So we want the difference between the axis and each of our data points, which if we pick a data point here, or value here, then it's always the 3 minus whatever that value is. That's how far away those two are from each other. And that's why we pick 3 minus x as our radius function. That might be one of the more difficult aspects in this particular chapter, is working with the radius function is no longer just x. And then once we, from there, we just plug everything into our same shell method formula that we talked about before. So 2 pi integral from 0 to 3 as usual, and then the product of r and h, which we found was 3 minus x times x dx. And again, working from there, we would just distribute our x and then integrate the resulting expression. Okay. Part D. Now I'm actually I want to change part D. I didn't realize this when I first assigned it. This one says about the line x equals 6. I want to change it to y equals 6. Mainly because we haven't done any washer method problems yet. But I want to demonstrate a scenario where we need to use washer method. Okay. Okay, we're doing good on time. So we have the same shaded region from 0 to 3. Now, we're taking 6 as our axis of revolution. Now, this time we have a horizontal axis, so we know we can we'll eliminate shell method basically. Shell method we only want to use for vertical axes, as we did in part B and C. Rather, A and C. No, it was B and C. Sorry. Anyway, the other thing is that we see that there's space between our axis of revolution and the shaded region. So our interpretation there is we want to use a washer method. Knowing that we have a horizontal axis that already narrows it down to disk or washer, and from there it's a matter of if there's any empty space between the shaded region and the axis of revolution. And since we have that empty space here, that's why I would use a washer method specifically. Alright. Now the washer method, here we have to find two different radii, r of x and capital R of x and little r of x. Now, capital R of x is the distance from the axis to the far edge of the shaded region. Little r of x is the distance from the axis to the nearest edge of the shaded region, relatively speaking. So if we go from here to here, all the way across, this line is y equals 0, this line is y equals 6. So our radius here is just top minus bottom, 6 minus 0. So r of x, capital R of x is 6 in this case. Now, little r of x is the distance between our axis of revolution here and the closer edge of the shaded region. And again, top minus bottom, so we'll take 6 for that axis minus, this is y equals x, so we'll do 6 minus x. And that will be our little radius function. So our formula is pi times the integral a to b, and we'll use capital R of x squared minus little r of x squared. dx. So from there, we just plug in what we found. We found that our limits of integration are still 0 to 3. Capital R of x is 6. And little r of x is 6 minus x. What would be different in this case is we have to be careful about the arithmetic or the algebra here. We'd want to go ahead and square this expression first in our order of operations, but then this minus sign would then distribute to each of those terms. So we want to be very careful. So like in this case, we know we get 36 minus, if we square this binomial, we get 36 minus 12x plus x squared. And so that will be 36 minus 36 plus 12x minus x squared. And then what happens is the 36's cancel, so we're just going to end up integrating 12x minus x squared. Okay. And again, I'm on the test going to want you to carry through those integrations and actually find the value. But for the purpose of this problem, so it wouldn't take too long, and the integrals of these expressions being simple enough, I think we'll be okay, at least as we're going through this, leaving them not quite finished, but I've done them, or I've shown you the most involved or complicated parts, I guess. Alright. So that takes care of the volume of revolution problems, and we did 6 examples basically, but again only 4 on the exam, and probably you can bet they're kind of like that last problem, although I'll give you a different region for each one. Is that one disk method, one washer method, and 2 shell methods. You probably expect something along the same lines. Okay. Let's go to page 481 next, because the next topic is in the chapter, if we're going in order, the next topic is actually the material from section 7.4, which is the arc length problems. That was 481. Not far enough. One more. Okay. And on this page I assigned 7 and 13. Now, probably these are already homework problems at one point, but let's go ahead and look at page 481, number 7. And this one appears to be integral from 0 to 1. Now, this specific problem gives us a graph right here, and we can say it starts at 0 and ends at 1 based on where it's shaded right here. But probably I'll give you the limits of integration as part of the question, so don't worry about that too much. And that one we just had to read the graph anyway, so it's not a huge deal, but I will go ahead and give you the limits in the question itself. Okay. Now our arc length formula is the integral a to b of the square root of 1 plus f prime of x, and that term squared, and then the square roots outside of that, dx. Sorry. Now, this is our f of x right here. This entire expression that we have. So we could say f of x is 2/3 times x squared plus 1 in parentheses, so 3/2, and we need to find its derivative to plug it in here. So f prime of x, we know this is a power rule. Actually, it's a chain rule if we want to be more specific. And in the chain rule, we do the outside part first, which is this exponent. So we take 3/2 and multiply it in front. We then decrease the exponent by 1, and then multiply by the derivative inside the parentheses, which the derivative of x squared plus 1 is 2x. Now the nice thing about this particular function is the 3's and the 2's will cancel each other out. And so we're just going to have the x squared plus 1 to the 1/2 power and then the 2x. So if we want, we could express that as 2x square root of x squared plus 1. And then that would be accurate for f prime. But now we want to square this to plug it into this formula. So if we want f prime of x squared, because these are multiplied together, we just square each term individually. So 2 squared is 4, x squared is x squared, and then that's times x squared plus 1, square root being squared, so we can think of it as 4x squared times parentheses x squared plus 1. Because squaring this term gets rid of the square root. Okay. We can go ahead and distribute that too. 4x to the 4th plus 4x squared. We'll have to do that at some stage in this problem anyway, so we might as well do it now. And so this expression now is going to plug back in for f prime of x that's being squared. So L equals integral 0 to 1, and then we have square root of 1 plus this expression, which is 4x to the 4th plus 4x squared dx. Okay. Now, this expression that we need to integrate, we see that there's some issues here. But what we can normally expect in an arc length problem is that there will be some way we can actually get the square root. Now remember, if we have a square root of a sum of terms, we can't just take the individual square roots of each term. That would actually not be correct. In particular, in this case, it would not be correct. So we want to make sure we take the square root of the whole thing in an entirety. But this is where factoring comes in handy. Now, when we look at 4x to the 4th plus 4x squared plus 1, and we set up a factorization for that, we know 4x to the 4th is 2x squared. And the way that we can factor a plus 1 is always 1 and 1. And so the issue is this correct as the factoring of this expression? And yes, it's true. If we multiply it back together, we can verify 2x squared times 2x squared is 4x to the 4th. 2x squared times 1 on the outside, 2x squared times 1 on the inside, that adds up to 4x squared, and then 1 times 1 is 1. Now the way that the reason this works out is that we actually get identical factors here, so we can write that as a single binomial that's being squared. Okay, and so that's great in this case because we have a square and we have a square root, so those are just going to cancel out. Okay, and so it leaves us with an integral of 2x squared plus 1 from 0 to 1. In this case, it was just a simple matter of factoring the expression that we were given. There will be other cases, though, where it's a little bit more involved, and I think the other example that I have for you in this section, which is number 13, I think, yeah, this is the more involved problem. So between these two, this is the kind of variety we can expect. Now, one of the nice things here, it's possible I could give you some kind of trig function at this stage that we would use to plug in here. Because if you remember, some of our trig identities have 1 plus a function squared. And so we can apply one of our trig identities here, plug in that expression, and then take its square root. Ultimately, in every one of these arc length problems, there should be some way we can take whatever expression is under the radical and write it as a perfect square. Whether it's just rearranging the terms like we did here, and then setting up a factorization, that's pretty straightforward. There'll be we'll see a different approach on number 13, so I'll hesitate to explain that just yet. And then the third approach I wanted to bring up, which you may see on your test, is one where if we have a trig function for y, and we take its derivative, and we plug it in, and so we get an expression squared, then there are identities we can use to utilize that. I don't remember if I did that for that part of the exam or not. Anyway, and it may be that I end up only giving you one arc length question instead of two on the exam, which would be kind of nice because that drops the exam down to 10 problems, so each problem is exactly 10 points. There's some benefits from a calculation standpoint there, but I still may consider a second one. Oh, sorry about that. So we have the integral 0 to 1 of 2x squared plus 1, and that's down here at the bottom. And so to complete that integration, okay, integral of 2x squared will be 2/3 x cubed. Integral of 1 will be x. That's from 0 to 1. So if we plug in x equals 1, we get 2/3 times 1 to the third. 2/3 plus 1. And then 0 gives us 0 and 0. And finally, just combining 2/3 and 1 together, that's 5/3. So our arc length is 5/3 in this scenario. Okay. So let's look at 13 next. I did say 13 is kind of the other variety of arc length problem that we see. Here we have y equals x to the 5 over 10 plus 1 over 6x to the third. and that's integrated from 2 to 5. Again, essentially just giving us the limits of integration. Alright, now, again, the formula for arc length is the same. We'll need to find the derivative of this function and then square it. So before we take the derivative, I would like to rewrite this expression. Instead of saying x to the 5 over 10, let's say 1/10 times x to the 5th. And instead of saying 1 over 6x cubed, let's say 1/6 times x to the minus 3. I do want you to be careful here, because I see a lot of people that they'll take this whole thing on the bottom and move it up to the top. But the issue is that 6 doesn't have a negative exponent. 6 doesn't have any exponent, it's just a plain number. So when we see this 1 over 6, it's actually just a 1/6 factor. And we will leave the 6 in the bottom, but x, instead of putting x cubed on the denominator, we can move it up and make it x to the negative 3. That makes that term easier to differentiate, because we need to multiply by this number and then change it from there. So that's y, and so y prime then, we multiply by 5, so that's 5 over 10, which is 1/2, and then decrease by 1, so it's x to the 4th. Then we take negative 3 times 1 over 6. Now, negative times positive means we're going to have minus, and then 3 over 6 is 1/2, and then subtract 1 from the exponent, so it's x to the minus 4. So we have 1/2 x to the 4th minus 1/2 x to the negative 4th. And now we want to go ahead and square that expression. And so squaring that expression gives us 1/4 x to the 8th. So 1/2 times 1/2 is 1/4. X to the 4th times x to the 4th is x to the 8th. We add the exponents in that scenario. Then we take 1/2 times negative 1/2 times 2 to get the middle term. 1/2 times negative 1/2 is negative 1/4. Times 2 is negative 1/2. Notice when we multiply x to the 4th times x to the negative 4, that gives us x to the 0. That's actually the other part of that, so it's negative 1/2 x to the 0. However, x to the 0 is just 1. And then we square the last term here, so negative 1/2 times negative 1/2 is plus 1/4. X to the negative 4 times x to the negative 4 be x to the negative 8, because we add those together. Okay. So this will then be plugged into our formula, which I'll write over here. L equals integral a to b square root of 1 plus f prime of x squared dx. And so this expression we just found right here is going to be plugged in right here, because this is y prime squared that we found, and this is f prime squared, the same thing. Okay. Our limits are 2 to 5 as given in the problem. And we end up with 1 plus, and we have 1/4 x to the 8 minus 1/2 plus 1/4 x to the negative 8 dx. Now, we have a 1 and we have a negative 1/2, which actually combine to give us a positive 1/2. So we combine our like terms, and now from this point there's a couple of different paths we can follow. Probably the path of least resistance would just be to get a common denominator in these three terms and work with it from there. So for the numbers, we have a 4, a 2, and a 4. So our common denominator is 4 between those three numbers. But remember, x to the negative 8 is actually 1 over 4x to the 8th. So if you think about it, we have x to the 8 over 4 plus 1/2 plus 1 over 4x to the 8th. So 4x to the 8th is the lowest common denominator. Okay? So we want to get all three fractions with 4x to the 8th on the bottom. Line that up. Okay. Let's see. So from 2 to 5. Now, under our square root, we want all the terms to have 4x to the 8th as the denominator. Okay. Now, this one just has a 4 on the bottom, and so to get the common denominator, we'll have to multiply by x to the 8th over x to the 8th. So that'll make it x to the 16. This term has a 2 on the bottom, so we'll have to multiply by a 2, top and bottom, to get the 4, and by x to the 8th as well. So it's 2x to the 8. And our last term actually has the correct denominator, so we'll just put a plus 1 there. So all we've done to get to this stage is we've found a common denominator between the two terms. Now the reason that we did that makes the numerator factorable, and the denominator we can separate by just taking its square root. Now if we look at our factorization on the numerator, x to the 16th is actually just x to the 8 times x to the 8 plus 1, and the plus there means it would be plus 1 in both locations. And if we FOIL it out, we would see that we do in fact get the 2x to the 8th in the middle on the product of the results from there. So this is identical factors, so it's likely the square root of x8 plus 1 squared. So if we want, we can just write that as x to the 8th plus 1. You know, since we had two of them, we got rid of one of them by taking the square root. And then the square root for 4x to the 8th, the square root of 4 is just 2. And the square root of x to the 8 is x to the 4. Okay, remember when we're taking a square root of a term with an exponent, we basically just cut the exponent in half, so it's x to the 4. Finally, we're getting to a point where maybe it's not nearly so crazy. That's the hope anyway. But let's split this into two expressions, because we have x to the 8 over 2x to the 4th plus 1 over 2x to the 4th. dx. And so we'll reduce this. Now, x to the 8 over x to the 4, we can subtract the exponent, so it's just x to the 4, and that cancels the denominator. So it's really just x to the 4 over 2. And then for this other term, really it's just 1 over 2x to the 4th, so what we can write instead is x to the negative 4 over 2 dx. Finally, we can now integrate. I don't know, it might be better off making this part of the take-home as well. If you're looking at this problem, you're probably having some serious concerns. I may or may not include that on the take-home portion. I will let you know. Alright, so let's integrate. It's x to the 5, and then there will be a 10 on the bottom. Because if this is 5, then we multiply by 5 down here, so 10. X to the negative 3, if we add 1, make sure we change it accordingly. Adding 1 to a negative number means x to the negative 3. And then we divide by negative 3, so it's minus, and then we have a 6 in the bottom. Making very clear that that's a negative. Sorry. Okay. So, plugging in x equal 5. Five to the 5th power is 3125 over 10. 5 to the negative 3 power over 6. So 5 cubed is 125, then being to the negative would drop it down to the bottom. So 125 times 6 would be 750. And then repeating that for x equals 2. 2 to the 5th is 32 over 10. 2 cubed is 8, so we'll put that on the bottom, so it's 1 over 48. Okay, that's x equals 2. And from here, I would just use a calculator to put these together. It's kind of crazy otherwise. So 3125 over 10 minus 1 over 750 minus 32 over 10 and plus 1 over 48. And so that's the number the calculator gives. I don't remember what that denominator actually is. Sorry. Common denominator, let's see, if 750 and 48, those have a 3 in common and a 2, so they have a 6 in common. And that's it. So it would be 125 times 48. So we would want 6,000 times 309 3195. I bet that reduces though. There's no way that it doesn't reduce. Sorry. I don't know. Anyway, so we just leave the answer as a decimal. Well, actually, my other calculator should do the fraction better. Sorry about that. 3125 over 10 minus 1 over 750 minus 32 over 10 plus 1 over 48. Nope, it did the same thing. We'll take that as the answer then. Sorry about that. So that's 309.3195. Yeah, it's some crazy number. That's probably why it's like that. Okay. So that wraps up our arc length problem. And again, if it's going to be a problem like that, as opposed to the earlier problem number 7 that we looked at, 13 is a much more involved problem. I would probably give that as a take-home in that scenario. Okay. So what do we have left? On page 511, go ahead and we'll go ahead and skip 30 because I know that's the surface area of revolution problem. So we don't need to worry about that one. We went over in class, and that's fine. So what that leaves is 33, 38, and 43. 33 is on Hooke's law, and then 38 is on winding a cable, and then 43 is the center of mass of a planar lamina. We're almost out of time. Let me see how I can probably get through these pretty quickly. Maybe not the center of mass, but the first two at least. And I may just keep going so that the video is there for y'all to look at, where it has all the problems together. So, I mean, if you have another class you need to get to, it doesn't bother me if you need to leave, but I want to make sure I get through all this for the video, so the entire review is contained in one video. Okay. So number 33, again, this is Hooke's law. A force of 5 pounds stretches a spring 1 inch from its natural position. Find the work done in stretching the spring from its natural length of 10 inches to a length of 15 inches. So our first statement there, 5 pounds stretches the spring by 1 inch. Now, in this case, this allows us to use Hooke's law, F equals kx, to determine the spring constant, or the restorative force of the spring. Now, you may want to say, you may think, well, let's convert inches to feet. Well, everything else in the problem is given in inches, so we don't actually have to use feet throughout. We can just keep with inches, And our answer in our work done will be in inch pounds rather than foot pounds, and then we can make the conversion at the very end rather than at each step in the middle. Okay, so let's just keep using inches for now, but also remember that we are in inches. So 5-pound force, and we have a distance x of 1 inch, and so K is equal to 5. That's our restorative force of the spring. Okay, so that means that F equals 5x is the force function. So we establish that. And then we look at the next part of the problem. It says that we want to find the work done in stretching the spring from 10 inches which is the natural length, to 15 inches. Okay, well, if the natural length is 10 inches, then that corresponds to x equals 0. And then if we're just, if we're stretching it from 10 to 15 inches, that means we've shifted it by 5 inches from its natural 0 position. So this corresponds to x equals 0, then this will correspond to x equals 5 because they're 5 inches away. All right. And so this allows us to set up our work as an integral from a to b of our force function f of x dx. And our limits in this case are the distance we have to stretch the spring, which is from 0 to 5. We'll insert our force function 5x dx. And from there, it's a fairly straightforward substitution or integration. Integral 5x is 5x squared over 2 from 0 to 5. Now, the 0 is just going to give us a 0 when we plug it in. So it'll be 5 times 5 squared, which is 125 over 2. And then minus 0. So 125 over 2. And this is again in inch pounds. Now, since we're talking about an actual measurement of force in this case, or work, sorry, we'll actually want, instead of writing 125 over 2, it makes sense to express that as a decimal. So we'll go ahead and make that 62.5 inch pounds. And if we like, at this stage, we can take that 62.5 and then divide it by 12 to convert that to foot pounds if we prefer. Okay. Because there it's just a normal conversion from inches to feet, which is divided by 12. Okay. So that's 33. Next we have 38. Now in 38, we have a 200-foot cable that weighs 5 pounds per foot. right? And it's hanging from a winch that is 200 feet above the ground that is attached to a 300-pound load at the bottom. And so we want to find the work done in winding up the cable all the way and raising the load to the height of 200 feet. Okay. Now, our force function is based on two elements in this case, because the weight that's attached to the winch is based on the cable itself, which has its own weight of 5 pounds per foot, and the load that is attached to it at the bottom. So we want to look at the total load at start of the problem. So if we have a 200-foot cable that weighs 5 pounds per foot, the cable itself weighs 1,000 pounds. 5 times 200 feet. 5 pounds per foot times 200 feet is 1,000 pounds. And we have 1,300 pounds attached, or 300 pounds attached to it, so we end up with 1,300 pounds at the outset. Now our force function, that means we'll start with 1,300 pounds of weight attached to the winch, but every foot that we wind up, we lose the 5 pounds per foot that the cable weighs, because the less cable that's hanging from the winch, the less load it's carrying. So we're losing 5 pounds per every foot. So if after X number of feet, we've lost 5 times X pounds from the load that's hanging from the winch. So that's how we go ahead and set up that force function. Now the work done is the integral of the force function from A to B. Now A and B in this case are basically where the load starts and where the load ends. So it starts at 0 feet off the ground and it ends at 200 feet off the ground. So we want to find 1,300 minus 5x integrated from 0 to 200. Again, this is the most significant portion of these force problems, is actually figuring out the formula that needs to be integrated and getting the correct units of integration, both for number 33 and for 38. Okay. And so we get 1,300x minus 5 halves x squared as our integral, and that's from 0 to 200, so we plug in 200. 1,300 times 200 is 26 with 4 zeros, so 260,000. 200 squared is a 4 with 4 zeros times 5 over 2. Let's see. 5 over 2 times a 4 with 4 zeros, 40,000. So we get 100,000. And if we subtract those, then we get 160,000 foot-pounds of work that must be done in order to lift that load. Now, anytime we think of an example might be like a kind of a basic elevator. Although with elevators, it's more of a counterweight system, I believe. Um, so it's not like strictly, applying power to raise a load this distance, but it's kind of the same things happening if you want to visualize it that way, because we have the cable itself plus the load that it's attached to that we have to consider. And yeah. Anyway, let's see. So the last problem we want to look at is 43. And actually, I'll go ahead and start on this page because we'll probably need the space. And we want to find the center of mass. And the problem they give is y equals x squared and y equals 2x plus 3. So these two curves will completely enclose an area, and we want to find the center of mass of that area. So y equals x squared, we know that's a parabola through the origin. And 2x plus 3 will be a diagonal line that goes through line 3. And so we're able to find the shaded area here. And we notice that there are 2 points of intersection, and the points where these graphs intersect will be the limits of integration that we ultimately use. So to get those limits of integration, we'll just set the two equations equal to each other. X squared equals 2x plus 3. Because it's quadratic, we'll move everything over to the left. So we minus 2x minus 3 equals 0. We can factor that. X minus 3, x plus 1. And so we get x equals 3 as one limit of integration, and x equals negative 1 as the other. Okay, so we know we're going to go from negative 1 to 3. Our top function is y equals 2x plus 3, and our bottom function is y equals x squared. And knowing which function is on top and which function is on bottom is important, because that's how we set up our order. So we usually call f of x our top function. That'll be x, 2x plus 3. And g of x, our bottom function, will be the x squared. Okay. Alright, now center of mass, there's three things that we have to find. First thing we want is mass, which is just, mass is actually just equivalent to the area of the shaded region. So we know the integral is going to be from negative 1 to 3. And we'll just take the top edge minus the bottom edge, f minus g, which is 2x plus 3 minus x squared. dx. Okay, so that is x squared plus 3x minus x cubed over 3 from negative 1 to 3. And if we plug into 3, we get 9 plus 9 minus 3 cubed is 27 over 3 is 9. And at x equals negative 1, we get 1 minus 3 minus, it should be plus 1/3. So if we plug in a negative, we have 3 negatives and then a fourth negative. So 4 negatives make a positive. Putting that together, we know 9 minus 9 cancels. So we're going to have m equals, so we have a 9 minus 1 plus 3 minus 1/3. So that'll be 12, 11, 11 minus 1/3, which is 32 over 3. Okay, so that's our mass of this area, of this region. Next we look at mx, which is the moment about the x-axis, so it's -1 to 3 again, and the formula I gave you is 1/2 times f of x squared minus g of x squared. Okay. Now f of x was our top function, that was 2x plus 3. And then x squared was our bottom function, that's g of x, so that's x squared parentheses squared being subtracted, and then times dx. So 2x plus 3 in parentheses squared will give us 4x squared plus 12x plus 9 minus x squared squared, which is x to the 4th. And then we can go ahead and integrate that expression. 4x squared is 4/3 x cubed. 12x is 6x squared. Integral of 9 is 9x. And integral of x to the 4th is x to the 5th over 5. And that's from -1 to 3. And we don't want to forget about the extra 1/2 that we have hanging around. But if we plug into 3, let's see, that would be 3 cubed is 27. Divide by 3 is 9 times 4 is 36. 3 squared is 9 times 6 is 54. 9 times 3 is 27. And 3 to the 5th is 243 over 5. Then we repeat with -1. -1 cubed is -1 times 4/3 is -4/3. -1 squared is 1 times 6 is 6. Minus 9, or minus 9. And then -1 to the 5th over 5 times another negative makes it plus 1/5. Okay. So we get, so 1/2, and then let's see, we have 36 plus 54 plus 27, and then we have a -6 and plus 9. So now we're going to have 120. We know we're going to have minus 243 over 5. We'll have a plus 4/3, and then minus 1/5. So putting that all together, and then dividing by 2, gives us that result. 544 over 15 is equal to mx. Didn't say it was going to be pretty, unfortunately. Lastly, we need my, which, again, our formula is a to b, and we end up with x times f of x minus g of x. That's our general formula. And so integral negative 1 to 3 of x, f of x is 2x plus 3, g of x is x squared. Now, that's from negative 1 to 3, sorry. Go ahead and distribute the x first, so it's actually 2x squared plus 3x minus x cubed. And then we integrate which means we'll have 2/3 x cubed plus 3/2 x squared minus x to the 4 over 4, and that's evaluated from negative 1 to 3. Okay. So if we start plugging in those limits, we do 3 first. 3 cubed is 27. 2/3 of 27 is 18. 3 squared is 9, so that's 27 over 2. And 3 to the 4th is 81 over 4, so minus 81 over 4. At negative 1, we get negative 2/3. Plus 3/2. And this will be minus 1/4. Okay. So combining our like terms, I have 18, 27 over 2 minus 3 over 2, so it's 24 over 2, which is 12, minus 81 over 4, plus 1 over 4, which is negative 80 over 4, which is negative 20, and then we'll have an extra 2/3 added on. So this is 30. Minus 20 is 10, so it's 10 plus 2/3, which will make it 32 over 3. Okay, so there's our 3 values for m, mx, and my. Now x bar, we said would be my divided by m. So it'd be 32/3 divided by 32/3, so that's pretty straightforward. If we divide something by itself, it's equal to 1, so 1 is the first part of our center of mass. And for y bar, that's defined as mx divided by m, which is now more complicated. But we want to take the 544, not this calculator, other one. 544 over 15 divided by 32 over 3. So that'll give us 17 over 5. So the center of mass is located at 1 comma 17 over 5. Or if you like, we can, instead of saying 17 over 5, we can say 3.4. That might make better sense from a visual standpoint as far as looking at what it is on the graph. So 1 comma 3.4, if we look at the graph, 1 would be here. And 3.4 would be somewhere up in here. Probably what's happening on the graph is I don't have an aggressive enough slope, because at 3 this would have a value of 9, so this is going as high as 9 up here by the time we get to this point. So it looks a little odd to say, because I didn't graph it properly, but 1 comma 3.4. So if let me just do a little bit more appropriate graph. Go up to 9 there, and then 3 to the right, and we'll definitely 1 to the left. Now, there's -1, there's 3. Now our x squared graph, so 1, 1, 2, 4, and then 3 comma 9. And then our line goes through 3 and connects those 2 points. So we're saying our center of mass is somewhere right there. Which, that seems visually to make a lot more sense. So it looked at first that it was off, but with an appropriately drawn graph, it does seem very reasonable, I think. Anyway, so that is the review. And yeah, I will get that ready for you this afternoon, and it should be available later today to take the test. And you don't have to take it today. You can take it on Thursday during class time if you want, the in-class portion of the test, and then the take-home portion will also be uploaded. Now, the in-class portion of the test will be a quiz in the quizzes section, and once I load that in, it'll send you a message about the assignment being made, and if you have it set up to send you messages from Canvas. And the other thing I'll do is for the take-home portion of the test, it'll be in the files section, and so that will be there. Hopefully that is everything that we need for that. So hope everyone does well at this test, and good luck with it. Let me know if you do have any questions on any of these review problems before you take the test, so we can talk about those. And feel free to re-watch this review just to get look at specific examples again. Especially the in-class portion, I would recommend on the volume problems. You might want to look back at those if that's something that you feel like you're struggling with individually. Otherwise, good luck with it. And we won't have any lecture on Thursday, so I'll just be available to answer questions online if you have any. Yeah, no, that's a good question. I would go ahead and say yes. I want them both done by next Tuesday. Now the in-class portion, I'll probably give you a due date of Monday night at midnight, basically, or 11:59, and then the take-home portion just by class time on Tuesday. So yeah, you have basically 6 or 7 days to work on all of those things. Yeah. Okay. I don't think the take-home portion will be bad. I mean, the work problems I think you'll find not bad as far as the amount of time it takes. But definitely, like the center of mass problem, I wanted to give you time to just to do all the work, even though it's relatively easy integrations. All this stuff that took place here, it did take it's tedious work to an extent. So, I mean, it is what it is. So, yeah. So I want to make sure I don't want you to have to spend all kinds of time during a timed portion of the test working on that stuff, because just to be able to get everything correct, it does take a bit of effort, and I don't want you to rush through it, basically. Anyway, so I'll leave it at that for now. Good luck, everyone, and again, send me questions if you have them. I'll be ready to answer them. So once y'all get that turned in by Monday night, the in-class portion, I should have that graded by the end of the week. Yeah, by the end of that week, and I'll make sure that that gets put into your it'll be put into your grading canvas. So, yeah, so that is that. So, have a good day, everyone, and again, no class until next Tuesday, but make sure you have everything done by then. Okay, bye.